maybe video also. Video means it will show me, right? Here. Okay. Video review. Hello.
Yes, sir, you're audible, sir.
Okay, you can hear me. Okay, good.
Yes, sir. Naveen from NPTEL.
Okay, great. Hi, Naveen.
Yes, sir. Good afternoon.
He is also here.
Okay.
Okay, so we can start whenever ready, actually.
Yes, sir. I think participants are here, right? Other people are participants only, right? You can
Okay.
start.
Okay, great. So, hello everyone.
Hello, sir.
As you can see, this is me, Nirmal Raj, and here are your TAs, Akash, Jaya, and Deep. So please go ahead if you have anything to say, any questions. So if anyone has a question, you can unmute and just ask. You don't have to put it in the chat. Or if anything you want to discuss, we can discuss. This is the place to do it.
Hello, sir. Am I audible?
Yes, you are.
Sir, actually, in the first class, you demonstrate that what we mean by symmetry. There, you show a potential where U equals to minus G M1 M2 by mod R. There, you said that R that gives the rotational symmetry to the system. Then
Okay.
how that model gives the symmetry to the system? Can you please explain?
How is that giving a symmetry to the system, you are asking?
Yes, that mod R part,
Yes.
how that gives symmetry to the system.
So okay. So if you take a sphere, right?
Yes, sir.
Okay, let me start my video. Give me a second. Okay. So mod R means that it does not depend on the other coordinates, right? So in a spherical coordinates, you have both the azimuthal angle and the polar angle, right?
Yes, sir.
And the mod R. Mod R is basically R. We just write it as R in the spherical polar coordinates, correct?
Yes, sir.
So if a system, the potential of the system or the equations of motion depend only on that mod R, it doesn't matter which angle you are in, right? It doesn't matter what the theta and the phi is.
Yes, sir.
That is what spherical symmetry is here, actually.
But sir, you have said for this, if I mean, if an object is moving around the sun, then you say
Yes,
irrespective of any path that symmetry holds.
correct.
So, for elliptical path, let's suppose,
Yes,
then model
correct.
will be changed, na?
Correct, correct. So
So
what I was saying there is that you shouldn't be seeing what the particle is doing. Okay, that is not the symmetry that we are talking about here. We have to look at the symmetries in the equation itself, actually. Okay, the potential is spherically symmetric in this case. The potential has
okay,
spherical symmetry. Given that symmetry, anything can happen to a test particle in that potential. It can do an elliptical orbit, it can do a parabola, hyperbola, and leave the solar system, it can do whatever. That is not really the symmetry that we're talking about. We are talking about the underlying mathematical symmetry, not the phenomenon.
okay.
Okay? And that is the concept that we will be using again and again in this course. The underlying mathematical symmetry in the theory, which will give rise to phenomena. Okay, but we have to identify the underlying symmetry.
Okay.
Okay? Good question. More questions, comments?
Hello, sir.
Hi, yes.
Sir, am I audible?
Yes, yes, I can hear you.
Uh, Good evening, sir. First of all, thank you for such a wonderful course. I am
Oh,
Vibhor Khanna, and I am from ISET Thiruvananthapuram. So I have seen all the lectures up till uploaded. I have some bunch of questions. Uh,
please.
so, sir, so some of the questions might be very, basic and
Don't worry about it.
yes.
Yeah, don't
Sir,
worry.
honestly,
Huh.
I have understood most of the part, but one thing which actually troubles me is
Hmm.
that how are we actually seeing this concept of abstract group theory, which is of mathematics, and how is it related to particle? Like, I understood that there are these transformations, but
Yes.
how actually it was motivated for the first time, because what I feel is that your course, which I really liked, one point was that
Mm-hmm.
you are giving a very specific motivation to every next topic, which find is missing from most of the books. The
Mm.
only book I could find is Z, which actually talks about in this sense. But regarding this group theory, how it came to the mind for the first time, I am
Mm.
not very, easy
Mm.
with this part.
Mm. 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 So, okay, Vibhor, that is actually a terrific question. Okay, that's a really great question because this is uh, this is something that people don't have a good answer for even today, actually. Okay, that why is it that in physics something that seems to belong so much purely in mathematics, why is it that the universe is built with those symmetries in mind, right? Why the hell does SU3 even get into physics? That kind of a thing you're asking, right? So it's but then it turns out, that is really when you model field theory using these symmetries, somehow these symmetries are respected in nature and we ultimately do find experimental evidence for it. And then we're like, okay, it is there, and it is there for whatever reason, it is what it is. So another way to see it is, somehow physics makes use of all the mathematical structures available in mathematics. Somehow we see this again and again. And I can refer you to an essay, okay, by Eugene Wigner. It is called The Unreasonable Effectiveness of Mathematics in Natural Philosophy or something like that. But it has the word unreasonable effectiveness of mathematics. I encourage you to go read that, because it does seem unreasonable that all these amazing mathematical structures seem to have a place in the nature around us also. And people just use it. So you asked who was the first person who came up with this? How did we even get into this, right? I would point it to Einstein, actually. So Einstein, he did not. I'm sorry. Sure. Yeah. Yeah. So we'll put it in the chat. The name of that essay. So okay, how do we write this?
I think you can read. See here.
Okay. I'll just write it on the thanks. So the unreasonable effectiveness of mathematics in, I think it's called physical sciences. I'm not sure. So I'll just leave it here. But the main thing is written by Eugene Wigner. Okay, so how did we get into this business? So it began with Einstein, basically. He identified the Lorentz symmetry, right? That the laws of physics are invariant under all inertia. When you make a transformation to any inertial frame, that gave people encouragement to start looking for all kinds of symmetries. Then they started thinking about what are the other symmetries. And then people realized that this itself corresponds to a symmetry in group theory, which is SO1, 3. I think it will come in the lectures. And so people started looking for other symmetries, rotational symmetry and all that for space-time symmetries, but also internal symmetries. And then isospin came. Heisenberg came up with isospin, which is an SU2 symmetry, one of the smallest non-trivial groups. So this is how we started looking for these symmetries, and surprisingly, all these symmetries do exist in the underlying field theory structure. So that is the best answer we can give today, actually. Great question.
Okay, sir.
Yeah.
Sir, one more thing,
Yes,
that
please.
even in the last or second last lecture that has been uploaded, there you said that this symmetry actually breaks from SU2L cross U1 hypercharge to U1 EM. So first of all, correspondingly, you said that it is QED theory and electroweak theory. So my first question is that up till now, I used to think that these two theories are the same, to be honest, that QED theory and electroweak theory are same. So is there some major differences in that? And second of all, how this group theory is actually telling us something about the symmetry, and how is it actually breaking into some other group?
So the short answer, Vibor, is hold on. The symmetry breaking is coming up in full glory. In a few more lectures, okay, we will build up quantum field theory, and you will see that all sorts of symmetries and symmetry breaking we are going to deal with. And to answer that first question briefly, this is exactly where you will also see that the electroweak theory is actually a superset of the electromagnetism theory. The U1 that you get after breaking, right, so to speak, that breaking is the QED. The broken theory is the QED. The unbroken one is the electroweak theory. And exactly how this comes about, I would say just hold on for a bit. Basically, it comes down to being able to embed smaller groups into bigger groups. Okay, generators of smaller groups can be embedded into bigger groups. And that is where this comes from. But just hold on a little bit. It will come.
Okay, sir. Okay, sir. Sir, one thing which you put up a question in the very first of the lectures is that what can actually be considered a particle, right?
Yes.
And you said that anything can be considered a particle, even a pen, in the viewpoint of what we are studying. But
Yes.
in some of the last lectures, you said that there are field which are actually operators and which basically give rise to indistinguishable particles.
Yes.
So, sir, can't we now say that anything which is indistinguishable can only be considered a particle over all of the universe? Like a pen, like two pen,
Yes,
can be distinguished and
correct.
hence cannot be considered a particle, but two electrons cannot be distinguished and hence they are particles.
No, I would not say that. Um, that is why the context really matters. Uh, from the quantum field theory excitation point of view, what you say is correct. It will give rise to, particularly these fermions and bosons, which are indeed indistinguishable particles. In that sense, they are still particles. But we can obviously make composite particles, right? You can ask, is a proton a particle or not? It's made up of so many different things, and they're not indistinguishable actually. Of course, two protons are indistinguishable between each other, but um, but that line becomes murky, right? What is really a composite? Do you need to have distinguishable and indistinguishable composites? Not really, actually. So it's better to just say indistinguishable particle coming from quantum field theory and leave it at that.
Sir, one thing here
Yes.
that even the word this pattern you also used,
Which one?
that
Yes.
yes, okay, sir. So, sir, two protons actually they have three valence quarks, right? Up,
Correct.
and down,
Correct.
right? Cannot it happen that these two protons, which look indistinguishable, but don't actually have the same amount of patterns, and that can be a distinguishable factor?
No, that turns out not to be true. It turns out that when even the composite particles that we know are actually indistinguishable. That, because they are after all made up of more indistinguishable particles, right? So there's nothing that can form a difference between any two protons, actually. Ultimately, these are also formed with up and down and gluons and other things. And you cannot put them together in different ways. If you put them together in different ways, then there's a whole other particle, like the delta baryon or something.
Okay, sir. Sir, one doubt I had from lecture 16, that was this consequences of isospin, where you were telling about that why the proton and neutron states
Yes.
does not exist, right?
Yes.
There you talked about that this the psi3 part, that is the isospin part,
Yes.
should not be symmetric, right?
Correct.
Sir, the thing was that in my mind,
Hmm.
that since these two will be a bound state, right, of a proton and proton, and both are fermions, and
Hmm.
basically forming a bound state that comes out to be a boson, right?
Yes, correct. Yes.
So in that sense, this overall state can be symmetric of proton.
So, yeah. So okay. That's not what we mean by symmetry, right? When we say symmetric and anti-symmetric, we mean in terms of exchange only, right? So when we say overall symmetric, right? If I take this overall PP bound state, which is a boson, and then I take one more overall PP bound state, which is another boson, and if I exchange those two, sure, I should get a positive sign in the wave function. But that is not what we are talking about here. Whether the composite itself forms a boson or a fermion, whatever you exchange, when you exchange the constituents, what happens to the wave function is what tells you whether it's a fermion or a boson. So you should only consider the exchange of the proton and the proton.
Okay, sir.
And then
Uh,
think about all the wave functions possible. Spin, isospin, actually even color is there, but we don't care. Okay, spin, isospin.
Okay.
And
Sir, in this
yeah.
one of the book, either this P.P. Palash or this Griffith's book, there
Hmm.
is this one chapter by the name Three Quark Model, where it first tells about the SU3 model of quarks,
Mhm.
right? I
Mhm.
had one doubt, it might be very silly, that is it because they are considering only three quarks in the starting, like up, down, and strange, and then they are talking about other quarks and
Mhm.
accumulating it into this model? Or why do we take SU3 first?
Good question. Yes, indeed, historically, because these were the first three quarks discovered, and these are the lightest quarks also. You, no, until that point, all the mesons and baryons that they had found contained these quarks in some combination or the other. And to understand the patterns of those baryons and mesons, uh, you can just use the three quarks, just these three quarks, and put these three fields in some SU3, make them rotate into each other in the SU3 space, and you get nice predictions for all the spectra and the properties and all that. That's the baryon octet and the meson octet and the decuplet and all that, right? That is the three quark. But now, that is still useful, but now we know better that there are more quarks and that the symmetry is not really exact and all that.
Okay, sir. Okay, sir. So, sir, shouldn't it be like that if there are 6 quarks, then it should be
Yes,
told by SU6?
correct. Absolutely. The thing is, even SU2, right? Suppose you take only the first two quarks. Even if you take just SU2, which is nothing but isospin, right? Even that is not a good symmetry, because the symmetry to be exact, you need the quarks to have the same mass. But all the 6 quarks have different masses, right? So start from SU2, that's not such a great, that's not a very good, it's a good symmetry, sorry, but it's not an exact symmetry. Then you add the strange quark. The strange quark is actually kind of heavier than the up and the down quark. So the symmetry is broken a little bit more, but it's okay. You tolerate it, and then you call it an SU3. Then you add the charm quark. Now the charm quark happens to be much heavier than any of these three. Okay, it's a whole other order of magnitude. So now you can do an SU4, but it's already becoming a bad approximation. Then you add the bottom, it becomes an even worse approximation. Then you add the top, there is really no approximation to talk about here. The top is 100 times heavier than all these other guys. So some people, right, in some contexts, actually they do put in an SU6 also to derive some relations in the meson, the bound state toponym spectra, things like that, basically. But it's not such a great way to do a calculation at that point, basically. The approximation becomes worse and worse.
Okay, sir. Sir, can you tell me that these two terms, to be honest, are not very clear to me. Good symmetry, exact symmetry, approximate symmetry.
Okay.
Somewhere I read that this chiral symmetry is not a good symmetry to strong forces.
Correct.
Somewhere I read. So
Yes.
what is this meant by this good symmetry or being an
Okay.
exact symmetry?
Good. So the short answer is, when we get to learning more about symmetries in field theory and symmetry breaking and all that, right? There we will see in exactly what sense we say approximate, good, and all that. For now, just think of it this way. The quark masses are different, right? So you take that difference, that difference will somehow get reflected in the final result that you're getting. If you want to calculate the meson masses, there will be a discrepancy in the meson masses also. You have to take the absolute mass of the mesons and see the difference between them. If the fractional difference is like 5% or something, right? Then you are like, okay, fine, it's a good symmetry. It's just a judgment call at some point. Okay. But we will quantify this a bit more precisely when we get to symmetry breaking in the course.
Okay, sir. Okay.
So
Sir,
can I something? So Vibhor, since many people are here,
okay.
I'm gonna throw the floor open for others to ask questions, and then
Okay.
we can come back to you. Is that fine?
Okay, sir. Sure.
Okay. These are good questions. Just keep them in mind. Does anybody want to speak up and have more questions? It doesn't even have to be a question. It can be a comment, criticism, concern, feedback.
Sir,
Yes.
sir, can you say more about baryogenesis? You bring that topic in lecture 3. So I'm not too far to the lecture. I'm just started. So
Okay.
you said the variogenesis created symmetry. So can you say more about that?
Sure. So one thing I want to say here is we won't cover baryogenesis in this course. It is more like particle cosmology. But okay, one quick thing is on cosmological scales, right? On the scale, if you put out our telescopes and measure how many baryons are there, when we measure all the galaxies from everywhere and all that, on those very large scales, we see only matter and not much antimatter. In fact, no. In fact, we almost never see antimatter on the largest scales. Okay, so that makes the question: why are there only so many baryons, and where are really the antibaryons? And then we can extrapolate this back to the early universe and ask how many baryons should have been for every antibaryon. Okay, so there seems to have been some asymmetry in the past. And that really is a mystery because there is no reason to start with one over the other, right? There is no a priori reason to have started with an asymmetric population because there's nothing in the theory that gives you that much asymmetry. So if things had started symmetrically, then the baryons and the antibaryons should have by and large annihilated with each other, and you shouldn't have an asymmetry to begin with. And the standard model does not accommodate the level of asymmetry that we see. That is really the problem. Okay. But it's a big topic on its own, and I would encourage you to go read some reviews and all. There are some nice reviews and articles on these things.
Thank you, sir.
No problem. More questions? Discussions?
Sir, can I ask?
Yeah, go ahead, Vibhor. Yeah.
Sir, this one of very basic things I had in mind that we know that only mesons and baryons are the bound states of quarks which exist, okay?
No,
Due to some
no, that is not true. I don't know if I said that in the lecture. You can have more. You can have tetraquarks and pentaquarks.
Yes. I was going to ask about this only that like what I thought is true is that due to this some color neutrality thing,
Yes.
these two can be formed. But
Yes.
I saw a paper by this Atlas, I guess, from 2020 that
Yeah.
they have observation of structure in JSI pair mass spectrum, which tells about that they have detected tetraquark
Correct.
bound state. So, sir, like what is the correct thing that can we have more bound states of pentaquarks, or why
Yes.
can't we find them, or what is the reason behind that? Mostly we see mesons or baryons.
Mm-hmm. Okay, so for this also, let me say this. So when we get to the group theory parts, right, in the lectures, when we talk about the symmetries and SU3, and then I'll talk about fundamental representation and all that. I don't know if that's already come in the lectures. Okay, I will talk about fundamental representation, anti-fundamental representation, and things like that. When we get to that part, I encourage you to ask this question again in the forum. Okay, because as far as I know, that is the only way to answer this question. You have to ultimately take these quarks, put them together such that you end up with a color singlet. Because color singlets are the only naturally occurring bound states that we find anyway in nature. Okay. And the simplest color singlets one can form are, of course, a meson, where you take a quark and an antiquark, it will form a color singlet. Another color singlet you can form is if you take 3 quarks, no antiquarks, just take 3 quarks, put them together, you will form a color singlet. Okay. So, but yet another way is to take 3 quarks and put them together with an anti-quark, there is a way in which you can form a color singlet with that also. And this is something I am not able to answer now because I have to tell you what a fundamental representation is, how you can get direct products and all that. And this is something I touch upon in the course. Okay. So that is the game ultimately. To form color singlets, you have to put some combination of quarks and antiquarks together in order to form color singlets. And a tetraquark is this. If I remember correctly, it's 3 quarks and an antiquark. It can form a color singlet. A pentaquark is 3 quarks and 2 antiquarks. It will form a color singlet. In this way, you can form, anything you want. You can have 21 constituents with the combination of quarks and antiquarks. As long as you put the Lego blocks together correctly, such that you form a color singlet, it is there in principle. Now, these are just harder to find in nature, because now you are putting together so many constituents that the entire composite becomes more and more unstable, right? For the same reason that uranium is more unstable than helium, because you're now putting so many neutrons into this mix, and so many protons, so that there's a lot of Coulomb repulsion, and it just becomes more and more unstable, right? Even the residual strong force is not able to hold them together and all that. Similarly, when you put a lot of quarks together, there's a lot of Coulomb repulsion. You're squeezing them so close that there's also strong repulsion and so on. So these are just unstable. So the best you can hope for is to produce them temporarily in some collider. And when they decay, you have to make a lot of them so that you get a statistically large sample to be sure that you really produced it. And then they will decay every time, and you catch the decay fingerprints and get to see them. But they're there, actually. All these tetraquarks and pentaquarks are there. It's just hard for us to.
Okay.
Incidentally, right, also squeeze gluons together and form a bound state. Not just one. That is also a color singlet. It's called a glue bond.
Okay, sir. Sir, this one thing.
Yeah.
You used a word, this internal symmetries of a theory.
Correct.
So my question is that how to know that some symmetry is internal, or is there something known as external symmetry?
Yes.
And can there be more internal symmetries of a theory which are known to us, but which may exist? Like for this charge conjugation, when we faced a problem that of some decay, right, as you told in the lecture, then we thought that there can be an internal symmetry. So can there be more internal symmetries in nature which we know as of now?
Yes. So first of all, you got what internal was, right? External means if it acts in space-time, it's external. Rotations, boosts, these things are external. Internal means there is no space-time label to that. Like charge conjugation, there's no space-time label. It happens in your mind, where you replace the particles with antiparticles, right? So yes, the charge conjugation that you saw is just one example. Charge itself is an internal symmetry, right? Or global charge at least, like baryon number and lepton number. These are also internal symmetries. And we will go on to see more and more internal symmetries. Even isospin is an internal symmetry, because it's in your mind that you're like rotating protons into neutrons and vice versa, right? It's not happening in real space. So it's happening
So, sir, these are some actual things that we infer, or these are the things we introduce in our formalism to, make some understanding out of it?
To me, both of them are same, actually. Okay. This is what we do to model the phenomena that we see. And the best modeling tool that we have today is symmetries, in particle physics at least. So it's the same. You can call it either inference or, to make sense, you put it in, basically. So in terms of the symmetries, indeed, internal symmetries, you can actually put them in doublets or triplets or whatever, and that gives you these very neat predictions for the actual things that you measure, which are the masses and charges and all.
Okay, sir. Sir, this one thing that you use, that some are internal and some are space-time dependent symmetries. Aren't these the local symmetries?
So yes, they can be local also. That's the other thing actually. So even an internal symmetry can be local. It's
Okay.
just that
Uh,
it's not acting on space-time itself. It's just that it's a symmetry acting on the field internally only. It's a transformation on the field that is internal only, except that the internal symmetry itself varies from position to position and time to time. And so
uh,
it is a local symmetry in that sense. Nevertheless, it's an internal symmetry because it's not something happening in space-time.
okay.
Okay, so again, this also is a very good question again. So keep this question also in mind as we move deeper into quantum field theory. And then when I start building the standard model, right? And
Okay.
when we talk about gauge symmetries and things like that, right? There
Yes,
you
yes,
will
yes.
see even more detail actually.
Sir, even this in the last lecture, last to last lecture only, which are being uploaded, you have started this part that I am going to now build up the standard model. So
Okay, fine.
there, those 3 steps which you have told,
Uh,
step 0 to understand QFT and this. So these are kind of the last 2 lectures
okay,
given.
okay.
And sir, this from this point which we were talking about the local symmetries, there is this one thing that to quote that these primary reasons for field is that laws of nature are local.
What laws of
So
nature are?
so
Local.
that the laws of nature should be
Oh,
local.
fine, fine. That local. Okay, okay. Locality.
So, sir, why this imposition we have to put that laws of nature should be local only? Why it is a necessity that it should be dependent on space and time only? There can be laws of nature which don't depend on this space and time. Like how I think in this form is that no matter in whatever frame of reference we go,
Yes.
but the speed of light is constant, right? So it
Correct.
does not depend upon the frame of reference or the coordinate system or space time which we are taking.
Yes, yes.
So why the laws of nature have to be local?
I don't remember the exact context in which I said the laws of nature have to be local. I don't remember saying that. Or I don't
Sir,
know. I don't know.
Sir, the context, if I could remember correctly, was when you were giving the motivation for fields. So
Correct,
you
correct.
said that, yes.
Yes, exactly. If anything, I would have said that. I don't know how I said it, but what I must have meant is that the whatever field theory that you are constructing, right, should respect locality. Because that is what we are seeing in the experiment, right? We don't see violations of locality except in entanglement, but let's not go there. But in particle physics, proper particle physics contexts, right, we see that all the measurements are local. They do respect causality as well, right? So in general, if your field theory itself contains non-local operators, that is very strictly constrained. So in that sense, I must have said that the whatever you infer from measurements, especially particle physics experiments, locality seems to be respected all over the place.
Okay, sir. Okay, sir.
Yeah,
Sir,
but
one thing
but in principle, there can be non-local phenomena also. Okay, there's really nothing that stops you in principle. We already know that entanglement and all is non-local, but we generally don't go there at this point. In principle, it can be.
Okay, okay. Sir, one thing I want to say, it's kind of a comment and not a question, that although I am liking the course, most of it. Like the main USP, which I would say, is that how you are proceeding from one topic to another, and that is giving me some sort of satisfaction that how we are motivating. But one criticism as a student which I can give is that
Yes.
some topics I think that you could have spoken even more, like that of theta tau puzzle. That was not very much clear to me. And
Okay.
even when you talked about this time reversal, discrete symmetry, even
Yes.
that part was I felt that you could have given little bit more time to it.
Okay.
Uh,
Okay.
yes, sir. Yes, sir.
Okay. 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 Yeah.
Yes, sir.
Thanks. Thanks for that. Yeah.
Just a small, sir, suggestion. Like
No, no,
I
thank you.
know
Thank you for that.
much less than you.
No, no, definitely, definitely. Yeah. I guess, you know,
And
there is a bias here also, right? So somehow when I'm teaching, there are some topics that I tend to like more. So I tend to talk about it more, I think. And there are other topics that I feel like
yes,
this is the scope of what this is. And I think it's just a natural bias. But your point is well taken. And that is why we have these sessions and all, right? Where we can talk about
yes, sir.
things that resonate with you. We can talk about that a little more, actually. So,
Yes, sir.
but
Sir, I
also,
am really
you know, if you like something, right? This is ultimately the point of all this is my goal with the NPTEL course and all this is for you students to inculcate more research-like thinking. It's not just learning.
correct.
So absolutely, when something seems more interesting to you, and if I'm not covering it and all that, right? You go, you know, go crazy about it. You go and read more,
Yes,
and
sir.
you know, you can
Yes,
always,
sir.
and then we have the discussion forum, we have these live sessions and
Yes,
all.
sir. Yes, sir. Sir, one thing also I wanted to ask that you
One
said
second,
that
sorry. So Vibhor, I'm going to actually one more time open the floor to others,
okay,
okay, and then we'll come back to you, just to see if you know there might be some new people who joined and all that. So the others here, would you like to speak up? Is there any comment or question you have? Now is really the time, actually. Nitendra, yes, please.
Yes, sir. So I have a question that initially we see that the up and down quark have SU2 symmetry and up down in distance is SU3. So we know from the Goldstone theorem or also the symmetry breaking part that you will cover. So
Yes.
initially these there is a difference between the masses of up and down quarks. So how
Yes.
do they have different masses? How can we say that they are manifestations of the same symmetry breaking?
Okay. Let me understand your question. You're asking how did the quarks even end up with different masses?
Yes.
Uh-huh. So that is an open problem. We don't know the answer to that exactly. Okay. But I'll give you a brief overview of what people generally think is the solution. The solution is that there is some other bigger symmetry. So it looks like there's an SU3 symmetry, right, between the U, D, and S. People suggest that all these might have been real symmetries at some high energy. Okay.
Yes.
That there was a particular pattern in which these symmetries broke, such that you ended up with the different masses. So the masses, after all, I don't know if you've seen this already. There are these Yukawa couplings and all that. The Higgs couples to
Yes.
two.
Yes.
So
Third.
why are Yukawa couplings different? Why does the Yukawa matrix have that structure? And the answer is there might have been a larger symmetry group. Actually, it's not even such a large symmetry group. You might have a symmetry in the ultraviolet theory, in the high energies, that broke in a certain way. There's a natural way to model build this, such that you ended up with, you know, some of the Yukawa matrix entries became really small, some of them became really large and all that. And then when you diagonalize all this, the quarks end up with this wide range of masses in log space, the wide hierarchy of masses. And then after this has happened, we now look at this from the low energy world and we infer some more symmetries like the SU3 symmetry, SU2 symmetry, and all that. Whenever quark masses are close by, we call it an SU2, SU3. Okay, did that answer your question?
Yes, sir. Actually, I could not understand the part you said that from Yukawa coupling. Actually,
Okay,
in
that will come
so,
when we do symmetry break. When we do the Higgs mechanism and symmetry breaking and all that, right?
so actually, I am there is a parallel course in my institute on particle physics, so they have covered that.
Okay, okay.
So for the Yukawa coupling thing, that is between the spin half and scalar particles.
Correct, correct.
So how is that playing role for the quarks here?
So the quark masses come from the Yukawa couplings, right? The Higgs has a coupling to a left-handed quark and a right-handed quark, the Higgs field.
Yes.
And then that coupling constant in front of this term is nothing but the Higgs Yukawa coupling. Okay, and then when the symmetry breaks, you have to, instead of the doublet, now you have some vacuum expectation value, right? So the Yukawa coupling times this V, the vacuum expectation value, that is nothing but the quarks. Is that clear? I'll write it actually. Yeah.
Okay.
So, okay, so you have terms like these, right? In the, I'm not going to put flavor indices first. So you have the Higgs, and this is probably a D, I think. Okay, I'll just put a U. Okay, so you have terms like these in the standard model Lagrangian, right? Now I'm going to put flavor indices. So I is some flavor, J is another flavor. Okay, and the coupling in front is the Yukawa coupling. Now, when you have symmetry breaking, you will end up with, some left-handed quark and then some right-handed quark. Let's call this UR. Then the Higgs will turn into some V, right? So this is not like a mass term, right? I'll put UL bar to be clear. So this is a mass term. The Higgs will become like a V, and then here I have a Yukawa coupling, right? This is the quark mass. Okay. So since the Yij's are generically different, and we don't know where they came from, you will end up with different quark masses. That is the ultimate source of this difference.
Hello, sir. Can you please once again? Actually, I was not able to see where it was all writing.
Oh, can you see the screen now, actually?
Yeah.
Okay, okay. So there it is in the screen. I've written in the first line, I've written the Higgs Yukawa coupling.
Okay.
The arrow is for symmetry breaking.
Okay. So.
And then I end up with the mass term down here. Okay. So since the Yij's are different in general, get different quark masses.
Okay.
More questions? More comments?
Yes, sir.
I think
Sir,
we
can I
start
ask?
also. Yeah. Yeah, please, Vibhor.
Sir, in this one place you said that you use the word free parameters of the theory for
Yes.
the mass, I guess. Mass and one more thing, if I remember, coupling constants.
Correct. Yes.
Sir, what are these free parameters? Like, what do we mean that we can choose anything in their place, or these are some kind of derived quantities?
Okay. Good question. Yes. It means in principle, you could have chosen anything in principle in the theory. But after you make experiments, you can actually, making measurements, you can actually trace them back to these parameters. And so you fix these parameters based on experimental values. Okay, so let's take an example, coupling constants, right? There's a coupling constant for QED, and there's a coupling constant for there are coupling constants for Eldrovich theory, and there's a coupling constant for strong force, right? Now, these are, when you write down the Lagrangian and all that, I don't know what these numbers are actually. These are all dimensionless quantities, right? That's another thing. That's another thing which is very strange about them. There's something in physics that has no dimensions. So you write down these, constants basically, right? So in principle, I don't know what these numbers are, but I can always make these measurements of particle collisions and annihilations and so on, measure the cross sections, and from the cross sections have a relation to the masses and the couplings, right? But the cross sections are the real thing. They're the real observables here, not the couplings. The couplings are all actually made up things in the Lagrangian. Okay. Using the actual observable data, you can trace them back to, because there are nice formulae between the cross sections and the these coupling constants, right? You can trace them back and fix what the coupling constants are. In that sense, they are free parameters. Now, why do we say free? So in the screen, I just wrote something, right? I wrote the Yij, and then after symmetry breaking, it became the quarks, right? So in a sense, the quark mass okay, how do I say this? In a sense, certain things are not free parameters, as in they are derived parameters. Like the quark mass is a derived parameter in terms of two free parameters, right? In the standard model, technically, okay, it says confirm you're speaking English. No, I'm speaking in English only. Technically, it's the Yukawa couplings and the Higgs vacuum expectation value, the V, those are the free parameters in the standard model. And this quark mass is a derived parameter. In the way I've written it, you can also rewrite it in a different way. Okay, in that sense, it's a free parameter. Is that
Okay,
good?
sir. Okay, sir.
Okay.
Okay, sir. Sir, one thing regarding the subject in general, I wanted to ask you, and this would
Yes.
be my last questions.
Yes.
One thing that I am genuinely concerned
Hmm.
is, as of now, whatever things we have studied in viewpoint of a master's graduate student in physics and mathematics in particular, what I feel is this whole of quantum field theory and this particle physics is bit different, but I see myself having the same approach to the subject, like studying it in a way that what sort of standard books are there, then seeing that what are the major topics being studied, what is like major content. But I find this thing missing in this subject, and as I have discussed with my fellow friends, like who have also studied this, I see that they actually focus on doing these calculations regarding this QFT and particle physics things. That is not my approach, to be honest. My approach is to understand the topic first, and uh, honestly, I'm not having very much satisfaction with these things. That do I actually understand this this how this kg equation and all of these things. So could you like speak about it a bit, that what should be the approach in general to this subject?
So actually, Vibhor, I am personally, right. My approach is also like your approach. Okay, I also try to like grasp it as much as possible intuitively. I try to get some whatever I was saying, get some intuitive feel for it and get to picture it and then put the calculation behind it, right? All I can tell
Yes,
you,
sir.
this takes time. Okay, so it won't
Okay.
happen in the first shot. You can try because these are, as you said, concepts that are so far removed from all the other kinds of physics that you have learned, right? These are not balls and springs. These are not charges going around other charges or anything like that, right? There's a lot of abstract stuff going on here. There's so many I, J, alpha, beta indices going on here, right? We write so many Greek letters and all that, and yet we call it physics. So it takes
Yes.
time to really see what is the intuitive bit behind it. So
Yes, sir.
do keep trying. At the same time, your friend's approach is also not wrong, actually. You should also calculate because these things go hand in hand. You try a bit, get some feel for it, but start calculating. You'll be surprised that the calculation gives you more intuition.
Okay.
Okay. In fact, in particle physics, there's no other way than to keep calculating. Intuition only helps you
Okay.
that so much. And then you have to calculate, and then the calculation will give you a whole new intuition because whatever we call intuition is only based on what we know in the past, right? But calculation is what will even expand our
Yes.
intuition.
Okay, sir. Okay, sir.
And so
Sir,
don't be so frustrated, is what I would say. I would even say that even at the end of this course, right, even after you write your exam and all that, you may not have grasped it completely, which is totally
yes, sir.
which is completely fine. You don't need to actually know, you don't need to know, master something completely in a course. But coming back to it, seeing it in different light, talking to people about it, this is how you keep building your intuition and become more and more expert.
Okay, sir. Okay,
It
sir.
will take time.
Because, sir,
But you have to be ready.
these,
Yes.
yes, even these small things like gauge actually keeps me up in night and actually troubles me from inside that, uh, do I really know what gauge is or all of these things? And what you said, I have
Yes.
actually experienced it myself because
Yes.
I have taken this course in the last semester of my master's. Okay.
Uh-huh.
But honestly, I didn't feel like that I know much about it. Like my approach is mostly to understand, read books, take classes, and make notes, rigorous notes. I
Yes.
have done all of this, but still I am not very confident with the subject, and
Yes.
that is why I found this a very good opportunity that you started this NPTEL course, and
Sure.
uh,
Yes.
yes,
You
but
know,
still,
I would recommend that, for you. So I have given this link to the actual course I taught in IISc, right?
okay, yes,
That
yes.
course, so it must be the discussion forum and all that, okay? Or you can go to my website and then there's a tab called teaching where all this is, the links are there.
Okay,
So
okay.
I can, my prescription to you would be, the thing that you've been doing is very good. That's a very good habit that, you've been making your own notes and all that. But there's nothing like solving problems. Okay. And the NPTEL problems that I give are not really, they're kind of simple problems. The assignments are simple. But if you really
Yes.
want to get deeper into it and get a real feel for it, you should solve the problems. And for this particular course, I have assignments tailored for this exam, the IAC exam I've given, the midterm exam, final exam, and
Okay,
all.
okay, okay.
I encourage you to go and actually solve those problems. The solutions are there,
Okay,
but
sir.
do it yourself
So, sir, I can find them on your website, right?
on my website, or even in the NPTEL discussion forum. I have given the link.
Okay, sir, I will definitely check them because I feel those MCQ questions which comes
Correct.
as assignment are not very helpful in building an
Correct.
intuition.
Correct. Yeah, that is just some very basic level testing. Absolutely.
Okay, sir.
For a student like
Okay, sir.
you, I think if you are this interested and if things keep you up at night, then I'll give you more things to keep you up at night. Go.
Sir, I am like very scared of solving these problems, honestly. But I will definitely give my 100% effort. I want to solve them. But what I have learned about myself from the coursework taken at Masters is that I get very scared from these.
No, nobody's testing you or anything,
Yes,
right? So this
yes,
is
yes, yes,
for yourself. So,
yes, yes,
because
yes, yes,
really
yes,
putting pen to paper and calculating is really where you learn a subject like particle
yes,
physics.
sir. Okay, 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 sir. Sir, these two things I want to share that one of the books from all major books that are there on QFT and particle physics, two
Yes.
which I like the most is this QFT for Amateur, Gifted Amateur. This book I am following mostly for QFT part, and this Schwartz book
Yeah.
for standard model and QFT.
Yes.
And this Peskin or this other book that you use a lot, Shrednicki. To be
Shrednicki.
honest, I don't like these two books
That's okay.
very much.
That's okay. I mean, everybody has their own.
Like
Uh,
if I'm following these two books, it would be more than enough, right?
I would say that, yes. I don't know about Gifted Amateur. I have not opened it. I'm an ungifted professional. But,
Yes.
but, but Schwartz, right, is more than enough.
Yes.
Schwartz and my notes and, to give intuition, the Gifted Amateur book should be good enough. Don't worry. Don't worry so much about books and all that. Again, Vibhor, your aim should not be to cover everything. Your aim should be to learn a few things very deeply. That is what will help you if you want to become a researcher.
Okay,
Don't
sir.
be
Okay,
bad
sir.
about
Okay,
not
sir.
knowing this, not knowing that. That is not the point here. The few things
Okay,
that
sir.
you should know them as deeply as possible and be able to calculate things in them.
Because, sir, one thing regarding this, I want to share that.
Yes. Can we make this a bit short because we are out of time now?
Okay.
Yeah, please,
Okay.
yeah, you can finish your comment.
Okay, sir. Okay, sir.
And then
Okay,
of course,
sir.
other comments you can write in the discussion forum or you can email me and all that.
Okay. Sir, I don't know if I should ask this here or not.
Okay.
That sir, like I have completed my master's and these days I'm applying for my PhD. Okay, I did a master's thesis in this particle physics only.
Okay.
But the thing is that what actually doesn't give me confidence is this part only, and I am thinking to master the subject first. So is it
Okay.
the correct way? I think this question would not be very much helpful to others because it is more of research oriented rather than the course that you are
Yes.
taking.
Yes.
So if you want, you can officially end according to
Okay.
the convenience.
Okay.
Yes.
Okay, why don't we do that? And why don't you email me this question?
Okay.
Maybe in a
Okay,
bit
sir.
also. And by email,
Okay,
I'll
sir.
tell you, I'll give you some answer, definitely.
Okay, sir. Thank you so much, sir. Thank you
Okay.
so much.
Yeah, no
Like,
worries.
sir, I'm really thankful for the time that this course has dropped on NPTEL. Thank you so much.
Thank you. Thanks for your feedback. And thanks to Krishna Kakal also.
Thank you, sir. I have the same query regarding the just calculating the steps. So what?
Yeah. So
Can you?
Nitin, we are out of time. Can you also
Okay.
email me your question actually?
Okay. Thank you, sir.
Okay. So
Participant can ask their question in Google Forum.
yeah, in the Google Forum is even better. More than email,
Yeah.
right? I would actually prefer the Google Forum because these are questions many people would have. So please don't be shy to ask in the Google Forum, okay? Nobody's judging anybody here or anything. Yeah, IISc link. So I think Parama is asking about the IISc assignment questions and all that. That link I have given in the discussion forum and in the announcement forum also. Okay, please go check that. I've given, I think the name of the title of the email is like course material full release or something like that. It has the word release in it. Go check that. But it should be there. Okay, great.
Okay.
Okay, everyone. Thanks so much for participating. These are great questions.
Okay, sir.
So,
Shall I end for everyone? Shall I make end for
yes.
everyone? Okay.
Yes.
Sir. Thank you, sir.
Okay. Thanks, Naveen.
Okay, sir. Bye, sir.
Bye.